So again, this is another recording that serves a dual purpose. One is to look at significant figures, units, errors, and so on, and the other one is it is a sample calculation for the lab on Unit 1 for density. So here I'm going to look at calculating errors. So these are the computational quantitative errors, and then later on in this recording I'm looking at random versus systematic, respectively qualitative errors. So let's start with the computational ones. By the way, this is the only time ever you're going to do this. After that, it will be just qualitative, that you're just going to say, well, this is what could have influenced my measurement, but you're not actually making calculation. So here's the only time that we ever do this. In order to, that is the computational errors, in order to determine the percentage error, I take my measurement error that I estimated at 0.05 centimeters and divide by 3.1 centimeters and shift the decimal point a couple of times, and that gives me the percentage error of that measurement. And then here I have 3 grams versus 350 grams. Again, I divide the two. That kind of looks like I've come up with a little bit less than 1%. So let me do the calculation. So first one is 3.1 divided by, no, not 3.1 divided by 0.05 divided by 3.1. So that's 1.6%. Remember, shift the decimal point. And that happens for length, width, and height in my case because I used a cube. And then it's 3 grams divided by 355 grams. And I come up with 0.8%. So that's what I have, 1.6%. Again and again, that's just because I have a cube. Notice that technically I should write the unit in behind, which is percent, but I already have written that on the top, and that's why I don't have to write it again. So those 4 errors, which I now add up at the percentage errors, so 1.6 plus 1.6 plus 1.6 plus 0.8 comes out to 5.6% of a total error. The 5.6%, I have to now look at what kind of error I have back here. So I have to take 5.6% of 12. Again, I'm going to look at, and again, I'm going to shift the decimal in order to actually calculate that. Okay, so here we go. 12 times 0.056. And that is 0.672. Because I multiplied my percentage as a decimal times the density of 12 grams per cubic centimeter, that is also why this one takes on the units of grams per cubic centimeter. And now, again, I have an overkill here of 0.672. I should round this to the ones place that I have here, the last significant figure, which is the ones place. So right here is where I should round it to. So I'm going to look at the next one that I have, the 6. So this one will round to pretty much just 1. And now look at my relatively large error, actually 1 gram per cubic centimeter. So it's 12 plus minus 1 gram per cubic centimeter. And look at the number that I had calculated in the previous recording that the calculator gave me, where I said, you know, this is a total overkill. And this number here, this computational error, justifies why I should get rid of all of this stuff here and then use this 1 digit here in order to round properly to 2 significant figures, which then 11.9 rounded comes out to 12 2 significant figures with an error attached of plus minus 1. Now, beyond that, I can also use my error of plus minus 1, and that gives me kind of error range. So actually my measurement could be anywhere between 11 and 13. And now I compare it to the density that I found from the book or on the internet, and it says 11.35. And I say, well, because of my measurement error, I didn't come up with the exact number, 11.35, but I came up with 12. But my error is relatively large, 5.6%. respectively plus minus 1, that actually the book value falls within my measurement plus minus the error. So somewhere between 12 plus minus 1. So that error range actually allows me to say that my measurement is actually pretty good. I'm relatively close considering that I have a relatively large error of 5 or 6%. Let's look at the one with the irregular shape specimen. Here the calculation is somewhat different simply because we're not just dividing and multiplying, but at some point we're subtracting. And here, even though 2 grams compared to 50, it's only a 4% error, and 2 grams compared to 45, that's also about a 4% error. That's relatively small, but we're subtracting these two numbers, and that's 5 grams. And now that error of 2 grams is relatively large. Take, for example, had I not measured 45 but 46, and had I not measured 50 but 49, now I have a difference of 3, and now my error of 2 grams is pretty huge. I have, of course, 50 and 45, but still the difference is 5 grams, and compared to a 2 gram error, that's pretty large. So divide the error by the error of 2 grams in this case by the difference of 5 grams, so 2 divided by 5. 2 divided by 5, shift the decimal point by 2, and that comes actually up to 40%. I have a pretty huge error, 40%. And that comes from that the spring scale for small masses, in this case a small difference in mass, does become relatively inaccurate. So 40% error, which I now attach to the 10, and of course 10 times 0.4 is going to give me 4. We can type it in the calculator. 10 times 0.4 is 4 grams per cubic centimeter. And now I say that, well, I came up with, I have to shift, or maybe I have to zoom out a little bit. Hold on. Okay, that may work a little better, comparing the book density of 7.4 grams per cubic centimeter to the density that I calculate of 10 plus minus 4 grams per cubic centimeter because of that relatively large error. Again, I'm in the ballpark. I don't want to say that I came up with the exact number here. I didn't, because my error is relatively large, but also because my error is relatively large, I can say I'm in the ballpark. I'm, given my error, not too far off. And again, I will actually do yet another recording and talk about qualitative errors.